Hi there! Welcome back to FE Civil Review Statics Part 2. Let's get to work. A two-member truss is loaded with a vertical load of 20 kips at node B as shown. The cross sections of the members AB and BC are 2 inches and 3 inches. Modulus of elasticity E equals to 29,000 KSI for both members. Calculate the vertical deflection at B. How do we calculate the deflection? Well, first of all, I'll go to the FE handbook and I will type truss deflection, and it's going to lead you to this formula, which is Fi multiplied by delta L, and delta L is shown to you as being capital F times L over AE. So let's write this formula down. So we've got that delta at B, at joint B, is going to equal to F multiplied by capital F multiplied by L, which is the length of the member, over AE. Now let's see what is the problem giving us. We are given the area of each member. So BC, the cross-sectional area is 2 inches squared, right? And then the cross-sectional area for AB is 3 inches squared. E is 29,000 KSI. In order to calculate the deflection at point B, we're going to start by first calculating the forces in each member. And we're going to do that by using method of joints here. So if I take node B, I have the 20 kip force pulling down, and then I have force, this is CB, and this is FAB. So if I do sum of forces in the y direction equals 0, I'm going to get FAB, the y component of force FAB is going to be equal to 10 divided by the hypotenusa, which I'm going to calculate in a minute. So we're going to calculate out of this right triangle. So AB is going to be equal to 10 squared, 8 squared plus square root of that. So I get 12.8. Okay, so now coming back to our equation, the y component of force AB, maybe I should show it here. So I'll have FABY, and then going this way, FABX. So sum of forces in the y direction equals 0. We'll have FABY minus 20 equals 0. Now, FABY is equal to 10 divided by 12.8 multiplied by FAB equals to 20. And from here, we can calculate for FAB is equal to, and you should get a value of 26.6 kips. And this is tension. Next, we're going to go to sum of forces in the x direction equals to 0. And this is going to give you minus FCB minus, now the x component of force AB, FABX equals to 0. From here, minus FCB is equal to the x component of force FAB is going to be equal to 8 divided by 12.8 FAB. So from here, we can say FCB is equal to minus 8 over 12.8 multiplied by FAB, which is 25.6. And calculating all that, you're going to get that FCB is equal to minus 16 kips. And this is compression. The minus sign tells us this is compression. Compression. So FCB actually, it has the orientation this way. The next step would be to calculate F, lowercase f, and the way to do that, you would remove the 20 kip load and add a unit load in point B, in node B. And since the 20 kip load is in the same node, we can find out the forces in each member A, B, and BC just by dividing the forces that we have gotten to 20 kips. So FAB is going to be equal to FAB divided by 20. Same for FCB is FCB divided by 20. And here we're going to get 25.6 divided by 20. We're going to get 1.28. And again, this is tension. And in here, FCB is minus 16. So we're going to get minus 0.8 compression. So now I believe we have everything we need to calculate for delta B. I'm going to come back here and I'm going to write F for, let's start with AB. So F, lowercase f, AB is 1.28 multiplied by force FAB is 25.6. Next, multiplied by the length of FAB is, we have calculated here, 12.8. A for member AB is 3 inches squared. So we have 3 inches. Now I have to be careful because the loads are in kips. This value here, 12.8, is in feet. So I'm going to add, multiply by 12 to transform feet into inches. So 3 inches squared here multiplied by E, which is 29,000 KSI. 1,000 KSI. So now we have 25.6 in kips. This is in inches, and KSI. So we're good now. And this is plus. Now we're going to go to member BC, and we're going to do the same thing. So lowercase bc or cb, lowercase f is minus 0.8. So we do minus 0.8 multiplied by the force of member CB or BC is this over here, minus 16, multiplied by minus 16. Then multiply by the length, which is 8 feet. Again, we're going to multiply by 12 to transform it into inches. And over, now the area of BC is 2 inches squared. So we have 2 multiplied by 29,000. And after you calculate all that, you're going to get that deflection at point B is going to give you 0.10 inches. And the correct answer is B. So a few steps you have to remember when you need to calculate the deflection at a certain node. You calculate the forces first in each member, and then you remove the force in that node and you add a unit load, and you calculate the forces in each member with the unit load, And then you need to know the length of each member, the area of each member, and modulus of elasticity. And we got 0.10. Let's move on. Find the area defined by the following expressions. Y is greater than 3x squared minus 2 and less than 5. And next condition is x is greater than 0. So here we're going to have to calculate the area defined by this equation one time, y equals to 3x squared minus 2, and x equals to 5. So what we have to recognize is that this equation defines a parabola, and then this is a line which is parallel to x-axis. So here first, let's find where this parabola intersects the x-axis. To do that, I'm going to take this equation and equal it to 0. From here, squared, I will have that x squared is equal to 2 over 3. And from here, x is going to be equal to plus minus square root of 2 over 3. So this parabola intersects the x-axis in these 2 points, minus 2 over 3, square root of 2 over 3, and plus square root of 2 over 3. So I'm going to draw the x-axis. Actually, let me move it a little bit closer here. I'm going to need a space. This is the y-axis, and this is the x-axis. And I can represent this line, which is parallel to the x-axis. I'm going to say y equals to 5. So I know this line intersects y-axis at 5. So I'm going to do this line is y equals to 5. And then the parabola, I know it intersects the x-axis. Let's assume this is minus 2 over 3, square root of 2 over 3. And let's assume this is plus square root of 2 over 3. There are 2 ways this parabola can intersect the x-axis. One way it can be upside down, or it can be like that. In order to verify that, I know that if A is positive, if A is greater than 0, I know that my parabola is going to look like that. So the ball is going to be full. So this, now I can show the parabola. I'm going to take another color. I know that the ball is full, so the parabola intersects the x-axis in these 2 points. And it keeps going. Another thing we have to find is what is the vertex of this parabola? Where does this parabola intersects the y-axis? For vertex, I'm not sure if this is in the FE handbook. X equals to minus b over 2a. So we calculate this. This is the value for x. As you know, our equation is 3x squared minus 2, so the b is missing completely. This is going to be 0 over 2, and a is 3. This is 0. And then the value for y, we just take the value of x and go to the y equation and replace x with 0 in this case. So we have 3 times 0 squared. Y is going to be minus 2. So now the vertex of this parabola, hk, if we want to keep it the same, is equal to 0 minus 2. So 0 minus 2, this is the point 0 minus 2. Perfect. So now that we have the parabola and the line represented on this coordinate system, we have to figure out which is the area, because we have to find the area defined by the following expressions. So we have found the line, which is y equals to 5, and the area defined by this line is everything over here, is this area over here. And then the area defined by the parabola is everything below the parabola. This is the area defined by this parabola. So what the problem is asking, what is the area defined by this expression? So it's asking the area, I'll make it in red, which is remaining over here. Another note is that x has to be greater than 0, so it's actually asking only the positive side of this. Does that make sense? So what we have to do, if you look at this graph, is we have to take the line y equals to 5, and then we have the equation of this parabola is 3x squared minus 2. And this goes from 0 all the way to this point, which we don't know what it is. So in order to find this point, we just have to take that 3x squared minus 2 is equal to 5. So we take these two equations and you make them equal. And this is going to be, moving forward, 3x squared equals to 7. From here, x squared equals to 7 over 3. And x equals to square root of 7 over 3, which is 1.528. So now we know the coordinates of this point, which is going to be equal to 1.528, because the y coordinate is known is at 5. In order to calculate this area, the problem is asking us to calculate over here. We're going to take, and it's only the positive side because we have x is greater than 0. So what we're going to do, we're going to take the area defined by the line, which is everything in red, in this purple. We're going to subtract the area defined by the parabola from 0 to this point only. So let's see, we're going to do this by do integral from 0 to this point, 1.528 of the following. So we're going to say 5 minus the parabola, which is, let me put 3x squared minus 2. This is going to be a square parenthesis, dx. And this is going to be equal, let's repeat this, 0 to 1.528 of do 5 minus 3x squared plus 2 dx equals to 0 to 1.528. And we have 5 plus 2 is 7 minus 3x squared dx. And now we can solve for this parabola. This is going to be equal to 7 dx, that is 7x, minus 3x squared, this is 3x power 3 over 3. And all this from 0 to 1.528. F0 is going to be 0, so we have FB, which is going to be 7 multiplied by 1.528 minus this 3 and 3 goes away, so we have x cubed minus x cubed is 1.528 cubed equals, and this is the area of that is asking that we have to calculate. So now from here, the area is equal to, let's do the calculation. and you'll get an area of 7.13. So the correct answer is C. I hope it made sense what we did here. Hopefully on the exam, you're not going to have such a complex problem. Moving on, find the centroid of the composite shape shown below. So the centroid of a composite shape, how do we do that? Let's go to the FE handbook. I want to see if we have formulas provided for the centroid, so it will give you a peace of mind. You don't have to remember it. Let's see if it does. I don't see it. Centroid. There you go. This is mechanical of engineering, but this is the formula for the centroid is eventually it's a sum of AI xi over sum of AI, or sum of area multiplied by x divided by sum of area. That's for the x value of the centroid, and then the y value of the centroid is a sum of area multiplied by y values divided by sum of areas. Okay, let's see. Let's write this down. X G, where is x equals to sum of I from 1 to n of AI xi over sum of AI. And then YG equals to sum of AI yi divided by sum of AI. In order to calculate that, I will have to separate this shape into different, let's see if I take this blue. So let's say this is shape number 1. Let's say this is shape number 2. And then we have 3 as the space here, the circle, and 4 is this triangle, the big triangle. And in order to calculate the centroid of this composite shape, we're going to have to assume a coordinate system. You can choose it anywhere you want. I'm going to have it over here. This is X and this is Y. And the best way to work in calculating the centroid of this shape is to actually build a table. And I'm going to build a table in a second. So we're going to build our table over here. Let's see, I have 4 shapes. So I'm going to draw 4 lines here. Okay, so this is the shape. And I have 1, 2, 3, 4. And next, I'm going to add the area. And then I will have X. And then I will have Y. Let me see if I can show this a better line here. Okay, and next I will have area AI multiplied by XI. Let's say this is I, and here AI multiplied by YI. Perfect. So let's start with shape number 1. We have this rectangle here, which is 10 by 20. So it gives me an area of 200. Next, I will work our second shape is this triangle, rectangle here, which is, so 30 minus 20, this is 10. And the height, this whole length here, is 10 plus 25 plus 20, which is 35 plus 20 is 55. So 55 multiplied by 10, this is 550. The next we have this circle, which is actually an area that doesn't exist there. So we're going to show it as negative, because we have to make sure to subtract it. So the area of this circle is PD squared over 4. and diameter is 16. So I have pi d squared over 4, and this is going to give you an area of 201.1. And then number 4 is this entire triangle, which is 40, and then this is going to be also 10 here, another 10. So the entire length of this triangle is 50. And the height, we have it as 55. So the area of this triangle is going to be half of 50 and 55. This is 1, 3, 7, 5. Perfect. Next, we have to calculate the xi, which is the distance from 0 to the centroid of each shape that we have chosen. So we have a shape number 1, the horizontal distance from 0 to the centroid of this rectangle is going to be half of this 20, so it's 10. Now the distance, the horizontal distance from 0 to centroid of this rectangle, it's going to be equal to 20 plus 5, so it's going to be 25. Next, we have the circle, and the horizontal distance from 0 to the centroid of this circle is 20 plus 20, so is 40. And now the triangle. When we know about the triangle, where is the centroid on the triangle? Is 1/3 from the base. So we're going to do 20 plus 10. That's 1 time. So we have 30 plus 1/3 of 50. So 1/3 of 50. And then we have to add 30 to that. So I get the horizontal distance for the centroid of this triangle, 46.67. We're done with the horizontal distance. Now we're going to have to find the vertical distance from the 0 to the centroid of each shape. So shape number 1, the vertical distance from 0 to centroid of this rectangle is going to be 10/2. So we have 5. Shape number 2, this is the other rectangle. We've got the total distance of this, the height of this rectangle is 55, so it's going to be half of 55. So I get 27.5. Next, I have the circle. Shape number 3 is the circle, and the distance from its centroid to 0, I have 25 plus 10, so is 35. And now the triangle, last shape, shape number 4, the horizontal distance from 0 to center of gravity of this triangle, it's 1/3 from base and then 2/3 from the other side. So we have 2/3 of 55, which is 36.67. And now we have to fill out this spaces here, AI multiplied by XI. So we're just going to multiply 200 by 10, which is 2,000. 550 multiplied by 25 gives me 13,750. Next, I have 201 multiplied by 40. That gives me an area, an AIXI of minus 804.2.4. And now 1,375 multiplied by 46.67 gives me an area of 64, not an area, but a value of 64,171.3. So now we can do the sum of all of this. Sum of AIXI xi is going to be 71,879. Now let's fill out this other part. We have 200, the area multiplied by 5. This is 1,000. We have 550 multiplied by 27.5. And this is 15,125. Next, we have 201.1 negative multiplied by 35. This is 7037.1. And finally, 1375 multiplied by 36.67. This is 50,421.3. And now if you do sum of that, you should get a value of 59,509. So when you add all of these values, the value for the circle is getting subtracted because the circle is actually not there. We have to subtract it. So now we have everything we need. We can come back to these formulas we wrote for the centroid of this composite shape, and is sum of AI xi, which we have over here. So we're going to have 71,879 divided by sum of AI. Oh, we have to do a sum of this as well. So let's add this up. We have 200, 550 plus, 201.1 minus, and 1375 plus. So I get a sum of area as 1923.9. So 1923.9. And this gives me the x value of the centroid, 37.36. Next, let's also calculate the y value of the centroid, which is 59,509 divided by 1923.9. And this is equal to 30.93. There you go. And this is how you calculate the centroid of an area. And if you would like to represent that, you can find the x value is 37.36. So it's going to be somewhere on this line over here. And then the y value is 30.93. I was to come here. This point is 35, and I have 30, so I'm a little bit below this. So I can just assume is approximately on this line. And then, so somewhere in this point is the centroid of this composite shape. And the correct answer, we have 37, 36, 4, and 3093. So the correct answer is D. Now let's move forward. Next problem is actually the same shape, and we have to calculate the area moment of inertia about the x-axis for this composite shape. And whenever you have to calculate the area moment of inertia for a composite shape, you have to start by calculating the centroid of that composite shape. And we don't have to do that because we have done that in previous problems. So I'm just going to write the centroid of this composite shape from what we have previously calculated. So xg equals 2 and yg equals, and I'll say 3736 for xg, 3736, and 3093 for yg. And the formula for area moment of inertia, or it's also called parallel axis theorem, it is given in the FE handbook, I might say several times. I think I've seen it. Let's see. Parallel axis theorem. There you go. So the formula for moment of inertia, area moment of inertia about the x-axis is Ix equals to the moment of inertia about its centroid axis plus the distance from the x-axis to the centroid multiplied by the area and the distance squared. So let me write this down. I'm also going to write down the formula. So Ix equals to, I'll say Ix about the centroid plus area of the shape multiplied by dy squared. D is the distance from the centroid of each shape to the centroid of the composite shape that we have found, and is the y distance. And then we have found that the centroid of this composite shape was somewhere here. So this is xg, yg. So this d distance for this shape number 1 is going to be the distance from its centroid to the centroid of the composite shape. I think we should get into actually calculating the moment area of inertia for this composite shape, and you are going to understand as we go. Okay, so let's say I'll say what ax, and actually, you know, after we do and calculate the area moment of inertia about the x-axis, and we're done with that, I'm going to let you and encourage you to calculate the area moment of inertia about the y-axis by yourself and see if you can get the results and write it in the comment section below. So ax for this composite shape is going to be equal to, we're going to come back here and let me clean this up a little bit. Oh, I did it too much. Okay, so I'll come back here and I'm going to write that this is the xg and yg. And then I will split this again into shape number 1, shape number 2. This is 3, the circle, and then this triangle is 4. Okay, so AX, the area moment of inertia of this composite shape is going to be equal to, we'll start with shape number 1. So I'll say I C of shape number 1, which is the moment of inertia of shape number 1 about its axis, which goes through the centroid of this rectangle, plus, and I will go with area of shape number 1, multiplied, and now the distance from its centroid all the way to the centroid, the vertical distance, right? From the centroid of this composite shape. So it's this distance over here. And this distance is equal to 3093 minus, and it's going to be minus 5 all squared. So we are done with shape number 1. Moving forward, plus, now we're going to take the moment of inertia of shape number 2. So I'll say about its centroid 2 plus area of shape number 2 multiplied, and now the vertical distance 55. Divide that by 2 is 27.5. So the distance from this centroid to the composite centroid is going to be 30.93 minus 27.5 squared. So this is shape number 2. Now let's go to shape number 3. And remember, shape number 3 is actually, it's an area that doesn't exist there. So we have to subtract. I'm going to say minus. And is the moment of inertia of the circle about its centroid axis. Plus, I'm going to do a parenthesis here so we don't mess this up. So I see 3 plus the area of the circle multiplied by the distance from its centroid. So I get 3093 minus, and this distance is 35. And it's okay that it's negative because we're going to square that. I guess let's put the square parenthesis. Great. Now moving forward, we're going to add the area number 4. And is the IC4 plus the area of shape number 4 multiplied by the distance from the centroid to the centroid of the entire triangle. And the centroid of this entire triangle it's 2/3 of 55, and this is 36.67, I think. So we can do 30.93 minus 36.67, and this value squared equals. So now we're done with all the shapes. All we have to do is substitute, which we're going to do here. And this equals, so I'm going to start with IC1, which is the moment of inertia of this rectangle. And moment of inertia of a rectangle, you don't have to memorize anything. At the end of statics, you are given the formulas for moment of inertia for various shapes. And I'm going to go to a rectangle, and AX about its centroid axis is BH cubed over 12. So I'll have BH cubed over 12 plus A1 multiplied by 3093 minus 5 squared. Now plus IC2, in this case, we have also a rectangle, so it's going to be equal to BH cubed over 12 plus, we're going to leave everything else the same as it is, A2 multiplied by 30.93 minus 27.5 squared. And now we have minus, and I will open the square parenthesis. IC3 is the moment of inertia of the circle about its centroid axis. So let's find the circle here. Now, of course, IX equals to AY. So it's PA power 4 over 4, and A is the radius. So I'll go here. It is PA power 4 over 4 plus area, this is area over 3, multiplied by 30.93 minus 35 squared plus, and now IC4 is the moment of inertia of this triangle, and I'll go back here, the triangle AXC, which is BH cubed over 36. BH cubed over 36 plus A4 multiplied by 30.93 minus 36.67 squared. So now the work to be done here is to substitute BH. Let's see if I have enough space to continue this. So BH cubed over 12. B for this rectangle is 20. So I have 20 multiplied by H is 10 cubed over 12 plus area is going to be 10 times 20. So I have 1,000 multiplied by this distance here, 3093, 5 minus 25.93 squared plus BH cubed over 12. Now we are talking about this shape number 2, and B for this shape is 10. So I have 10 multiplied by age, which is 55 cubed over 12, plus area number 2 is going to be 55 multiplied by 10, so it's 550. And then this distance, let's see, is 3093, 27.5 minus, so we get 3.43 squared minus, and now we're going to subtract PA power 4, and the radius is 8. So I get an area, and not an area, but a moment of inertia about its centroid of the circle, 3216.99. So I'll do 3217 plus area of the circle is pi multiplied by r squared. Pi r is 8 squared multiplied. So we have 201.1 multiplied by the distance from a circle centroid to the centroid of the entire composite shape. So I'll get 35, 3093 minus, get 407 squared. The way we wrote it, you get minus 407, and I'll write minus just in case, because it doesn't matter. This minus sign, it doesn't matter. It's going to be squared, so it does not matter. Now I'm going to close this parenthesis plus A4, so the plus, and now we have BH cubed over 36. The final shape, the triangle, B of the triangle is 50 multiplied by age, which is 55 cubed over 36, plus now the area of the triangle, which is 1/2 55 multiplied by 50. So 55, 50 multiplied 2 divided, I get 1375, and multiply by the distance, which is 3667, 3093 minus 574 squared. And again, the way I wrote it here, this is going to be negative, so let me just follow this negative, but it doesn't matter because it's squared, so that's why I don't really keep track of that. And now equals. So I did this calculation one time before this video, and I hope I did it right, because I got a value of, let's say, Ix of this entire composite shape equals to 551,087.8. So you do the calculations, and if you get something else, let me know in the comment section below, because I might have made a mistake. It's possible, but I hope I didn't. So the correct answer is C, 551,000. The closest is C. And let's move on to our final problem for today. We have belt friction. A fixed and a movable pulley are used to support a load of 120 kilograms as shown. If the pulleys are assumed to be massless and the coefficient of friction between the rope and the pulleys is 0.10, what is the minimum force F necessary for static equilibrium? So usually when we do a pulley problem, we assume frictionless pulleys, massless and frictionless pulleys. And when that's the case, we have the same tension on every side of the pulley. So we have T here, and T over here. Now, when there is friction present, the tension, it's not the same anymore. And the reason is because I'm gonna just draw a pulley here. Imagine we have the cable pulling on this side. And let's say This is force F. And let's assume that the system is going in this direction. There is going to be a friction force trying to pull the system in the other direction. So this is the friction force. And this is F2 or T2. And now, in order to write the equation of the equilibrium, F1 is going to be equal to F2 plus friction force. So now you can see that F1 is not equal to F2 anymore. Okay, let's delete this. And let's look in the FE handbook for the belt friction formula. So, right, belt friction, because you're given some formula in the FE handbook on belt friction. There you go. So you are told that F1 is equal to F2 multiplied by E power mu, which is coefficient of friction, multiplied by theta. Now let's talk about theta. I'll actually write this formula down first. F1 equal to F2 multiplied by E mu coefficient of friction power theta. So I'm going to go back to this pulley that I recently drawn and I deleted it, which I shouldn't have. So imagine if our force is pulling somewhere on the side. Let me do it this way. And then this one maybe goes down. So let's say this one maybe goes straight down and then this one pulls on the side, or it just can go anywhere. It doesn't matter. So whenever this cable is tangent to the pulley like this, this is the angle theta. Now, in our case, our cables are going straight down. So this is where the cable is tangent to the pulley. So the angle theta is going to be equal to 180 degrees in both cases here. So have a 980, which in radians is going to be pi. So pi equals to 180 degrees. Okay, so let's come back here to our system. Another important thing to remember and to note when solving this type of problems, we have to figure out which way the system is going. So look here, F1 larger than F2. So this is what it's important to note. So coming back here, the problem is saying, let's read the question again. What is the minimum force F necessary for static equilibrium? So in this case, before anything we add anything, this system is going to go down in this direction. It's going to go down this way. It's going to be pulled down this way, which means that this is the greater force, T3, this is T2, and this is T1. So now using the formula given in the FE handbook, we can write that T3 is equal to T2 multiplied by E mu theta, and then T2 is equal to T1 multiplied by E mu multiplied by theta. So now we can calculate E coefficient of friction multiplied by theta equals to E 0.10 multiplied by theta. So this is our theta in radians, it's pi. And you're going to get a value of 1.37. So now with this value, we can come back here and say that T2 is equal to 1.37 T1. And here we can say T3 equals to 1.37 T2. So now we have here two equations. Now looking at this system, if we are to draw the free body diagram of this system, we can say that this is our pulley. We have two forces pulling upwards. We have T3, we have T2, and then we have this force pulling down, which is the weight equal to 120 kilograms multiplied by G, which is 9.81 meters over second square. So the weight is going to be equal to 117.2, and these are newtons. So if we write the equation for this free body diagram, we're going to get that T2 plus T3 is equal to 1177.2. If we rewrite this equation and we substitute T3 with 137.2, this can be also written as T2 plus, and then we substitute T3 with the following: 1.37 T2 equals to 1177.2. And moving forward, this is going to be 2.37 T2 is equal to 1177.2. From here, we can calculate for T2 is equal to 1177.2 divided by 237. And this is going to give us a value for T2 of 496.71. So we have calculated T2, but we have to actually calculate this force F, which is Ft1, the minimum force necessary for static equilibrium. So we can come back to this equation now and calculate for T1. T1 is going to be equal, and this is actually from here, right? We have T1 equal to T2 divided by this value over here. So T1 equals to T2, which is 496.71 divided by 137. And T1 is going to be equal to 362.56 Newton. And this is our F. The problem is asking us, what is the minimum force for this to be in static equilibrium? And the correct answer is 360 Newton and is option A. That's all I have for you today, my friends. I hope you found it helpful. If you did, please don't forget to subscribe and give it a like, because this helps put this video in front of more people just like you. Please keep on practicing the FE problems, and I'll see you next week.